parametric algorithm. So for the non-parametric method, there is no hypothesis on pixel distribution. While the parametric method, they have distribution suppose continuous, and sometimes the distribution is normal. We call normal distribution. So this method affects on pixel considering the Euclidean distance to the class center, and some pixel cannot be classes if we fit the limited distance. Another method in the non-parametric classification is called parallelepiped method. So the parallelepiped method is a geometrical shape whose opposite sides are straight and parallel, and a parallelogram is a two-dimensional parallelepiped. It requires the least information by the user. The maximum likelihood classification, which is in the parametric classification, assume that the statistics for each class in each band are normally distributed and calculate the probability that a given pixel belongs to a specific class. Unless you select a probability threshold, all pixels are classified. Each pixel is assigned to the class that have the higher probability, that is, the maximum likelihood. If the higher probability is smaller than a threshold you specify, the pixel remain unclassified. So the maximum likelihood classification, you see here, the likelihood of the unknown measurement vector H belong to forest is greater than the likelihood of it belong to the agriculture. So assign the pixel to the forest. So for the below graphic, we assign the forest training data, and the unknown measurement vector H associated with the single pixel in the two-band multispectral dataset. And then we assign the agriculture training data. And so these two graphics, we show you how the maximum likelihood classification work. For unsupervised classification, they are commonly referred to a clustering, which is an effective method of partitioning remote sensor image data into multispectral feature space and extracting land cover information. Compared to supervised classification, unsupervised classification normally requires only a minimum amount of initial input from the analyst. That is because clustering does not normally require training data. Unsupervised classification is the process where numerical operations are performed that search for the natural grouping of the spectral property of pixel as examined in multispectral feature space. The clustering process results in classification map consisting of spectral class. The analyst then attempt a posteriori, after the fact, to assign and transform the spectral classes into thematic information classes of interest, for example, forest and agriculture. This may be difficult because some spectral clusters may be meaningless because they represent mixed classes of Earth's surface material. The analyst must understand the spectral characteristic of the terrain well enough to be able to label certain clusters as specific information classes. So there is your data clustering. So ISO data initial distribution of the 5 hypothetical mean vector using the first standard deviation plus or minus standard deviation in both band as beginning and end point. In the first iteration, each candidate pixel is compared to each cluster mean and assigned to the cluster whose mean is closest in the Euclidean distance. During the second iteration, a new mean is calculated for each cluster based on the actual spectral location of the pixel assigned to each cluster instead of the initial arbitrary calculation. This involves analysis of several parameters to merge or split cluster. After the new cluster mean vector are selected, every pixel in the scene is assigned to one of the new cluster. The split merge assign process continues until there's little change in class assignment between iterations. The T threshold is reached, or the maximum number of iterations is reached. So here the graphic will show you the figure A, the grouping of pixels of the 7 length cover class, and B, how this cluster compared to the 15 classes generated in unsupervised classification. And the last figure, C, show you how labels are then applied to the class. This slide shows you the difference between supervised and unsupervised classification. So for the supervised classification, we need to select the training field, and then we can evaluate the signature, and then we can classify the image, and we can evaluate the classification. For unsupervised classification, it is a little bit more step. So we need to run ISO data algorithm. We can also evaluate signature. We can classify image. We can identify classes. And then we can evaluate the classification. So both of the methods we need to evaluate our classification. So to evaluate our classification, we need to construct a confusion matrix. So here, a confusion matrix is a table that is often used to describe the performance of classification model or classifier on a set of test data for which the true value are known. So you have a kind of matrix which represent the ground reference test information and the remote sensing classification. The ideal situation is to locate the ground reference test pixel or polygon if the classification is based on human visual interpretation in the study area. These sites are not used to train the classification algorithm and therefore represent unbiased reference information. It is possible to collect some ground reference test information prior to the classification, perhaps at the same time as the training data. But the majority of test classification has been performed using a random sample to collect the appropriate number of unbiased observations per category. So we talk about the sample size. So the sample size is suggested by Fitzpatrick Lynn in 1981. He suggests that the sample size n to be used to assess the accuracy of the land use classification map be determined from the formula for the binomial probability theory. So as you see here, in the formula, P is the expected % accuracy of the entire map, E is the available error, and Z equal to from the standard normal deviate of the 1.96 for the 95% of the two-side confidence level. And for a sample for which the expected accuracy is 85% of the available error of the 5%, the number of points necessary for reliable result, which can be calculated here. You see the minimum of 203 points. So it is the sample size that we can choose for the evaluation of the classification quality. Then we can choose the sampling method. There are basically 5 common sampling designs used to collect ground reference test data for assessing the accuracy of a remote sensing derived thematic map. So there are random sampling, systematic sampling, stratified random sampling, or stratified systematic analyzed sampling, and the last one is the cluster sampling, as you can see in the different image in this slide. So the overall accuracy of the classification map is determined by dividing the total correct pixel. It means the sum of the major diagonal by the total number of pixels in the error matrix N. Computing the accuracy of the individual category, however, is more complex because the analyst has the choice of dividing the number of correct pixels in the category by the total number of the pixels in the corresponding row and column. The total number of the correct pixels in the category is divided by the total number of the pixels of that category as derived from the reference data. For example, the column total. This statistic indicates the probability of the reference pixel being correctly classified and is a measure of omission error. The statistic is the producer accuracy because the producer or the analyst of the classification is interested in how well a certain area can be classified. So it comes up with the question that what I see in the ground is on my map. If the total number of correct pixels in a category is divided by the total number of the pixels that were actually classified in that category, the result is a measure of commission error. The measure called the user accuracy or reliability is the probability that a pixel classified on a map actually represents the category on the ground. So it comes up with the question that is what I read on my map on the ground? It means that when we see in the map, is it those objects in the ground? So here you see an example of the confusion matrix, and to evaluate the classification quality. So the red color is the error of omission. The blue color is the error of the commission. And the green color is the producer accuracy. And the yellow one is the consumer accuracy. So we still ask the two questions. The first one is, what I see in the ground is on my map. And the second one is what I read on my map on the ground? We have another term we call kappa coefficient. So it's a kind of coefficient of agreement. The kappa analysis yields a statistic which is an estimate of a kappa. It is a measure of agreement or accuracy between remote sensing derived classification map and the reference data as indicated by the major diagonal or by the chain agreement, which is indicated by a row and column total as referred to the marginal. Now we look at another classification method we call object-oriented classification. So the basic principle is the method is cutting the image into object or by segment or by the segmentation process. And then it can describe of the object by the series of attributes in terms of spectral, textural, or spatial. And then we can classify the object. This step is only required if the spatial unit of analysis is the object. Segmentation is the division of the image into spatially continuous, disjoint, and homogeneous region, for example, the object. And segmentation of image into a given number of regions is a problem with a large number of possible solutions. There are no right or wrong solution to the delineation of landscape object, but instead meaningful and useful heuristic approximation of partition of space. So a type of segmentation that is very common in the multi-solution segmentation because of its ability to deal with the range of scale within a single image. So we have firstly the super object, and then we cut down into a sub object. For example, here you see an satellite image. And now we start to process the object-oriented classification. So first of all, we use to cut down into the major object. So here you see the super object that we cut down from the image. So you see the major object in different polygons. And then we cut down more into sub-object. So you see here a lot of smaller polygons. So you see here a lot of polygon with very detailed object. And now we start to do the object-oriented classification. So we cut down the super object. So you see here, and you see the polygon for different object. But as this region, we can easily identify, it means that all the objects are easily identified or differentiated. So we do only one step. So this is the final polygon of our object classification. There are some consideration on object-oriented image classification. In the object-oriented image classification, one can use features that are very similar to the one used on visual image interpretation. So we need to use the shape and size of the object and the spectral homogeneity within object and the semantic relationship of the spatial unit with its neighbor. So before the object-oriented image classification, there was the pre-field classification. In this approach, the objects are not extracted from the satellite image through segmentation, but instead from the extent of geographical data base with the landscape unit, for example, the field. Now we look at the change detection. So you see here, in a photo interpretation, we can analyze the change detection. So in these two photos, we have seen the land is changed from October 8, 1976 for the image in the left-hand side. And the right-hand side, the land is changed, and it was taken in 1978. So one method in the change detection is image subtraction. So it's a kind of image algebra change detection. So we have different image in different date 1, date 2. So we have a rectified thematic mapper band for day 1, rectified thematic mapper band for day 2, day 3, day 4. We can make a composite data set, and then we can different or band ratio image by threshold it to produce a binary chain or no chain map. So the advantage of image subtraction is normally does not require atmospheric correction, and it is efficient method of identifying pixels that have change in brightness value between dates. But there is disadvantage. No from 2, no change information available, and it requires a careful selection of the change, no change threshold. We can use another method we call multi-temporal color composition. For example, change detection in urban area. The left-hand side here, you see an Econo image was taken in 8 June 2000, and the spatial resolution for panchromatic is 1 meter, and for AS, the spatial resolution is 4 meter, and the sand extent is 11 by 11 kilometer. And the right-hand side is the QuickBird image, which was taken in 13 July 2003, and the spatial resolution for panchromatic is 0.71 meter, and AS is 2.84 meter, and the scene extent is 16 by 16 kilometer. So by using the multi-temporal color composition, for example, here on DVI Econo 2000, and DVI QuickBird 2003, and P QuickBird 2003, we can result in the color composition and we can see the change. We can detect the change by different color here. We see blue, yellow, or black. That show you the kind of detection. That show you the kind of change in the image in the area. So here is the result of the color composition image. So we can see the change. The green color, no, the sand color is the change from vegetation to building, and the magenta color is the change from building to vegetation, and yellow color is vegetation, blue color is building, and green color is shadow change, and light blue color is the building change. Here also example of the change by using multi-temporal color composition. So you see different image from different date, Equinox 2000 and QuickBird 2003, and we made a color composition, and so we can see the change. The blue, they had the change, and the sand color, they had the change in that area. Now we will look at the land use and land cover classification. What is the difference between land use and land cover? Land cover refers to the type of material present on the landscape. For example, water, sand, crop, forest, wetland, human-made materials such as asphalt. But the land use refers to what people do on the land surface. For example, agriculture, commerce, and settlement. There are classification scheme to classify the land use and land cover, which is mutually exclusive, mean that there is no taxonomic overlap or fuzziness of any class. For example, deciduous forest or evergreen forest are distinct class. There is exhaustive, mean that all land cover class present in the landscape are accounted for and none have been omitted. There is also hierarchical, mean that the sub-level class, for example, single family residential, multiple family residential, may be hierarchically combined into a higher level category. For example, into a residential class. That makes sense. This allows simplified thematic map to be produced when required. So here we show you the globe cover. The globe cover product as the first 300-meter global land cover map for the period December 2004 and June 2006. So if we want to know about the different type of the class in the previous slide, here is the region class of the global or level 1 globe cover region. So we have a lot of type coming from the post flooding or irrigated cropland, rainfed cropland, mosaic cropland, forest, mosaic forest, grassland, vegetation, or water body, or permanent snow and ice that you can see in different color in the previous image.
Let's check what you have learned so far. Click Start button to try the following quiz.
So we have learned about the supervised classification, which is one of the method for classify the satellite image. We have also seen the unsupervised classification that normally we call the clustering. And then we have seen the estimation of the classification quality by using different coefficients like kappa coefficient. And then we have seen how to detect the change. And finally, we have seen about the difference between land use and land cover and how to classify it. And we have seen finally the globe cover. It means the land cover the globe of our Earth. So it's all for the chapter. Now we are right at the end of the course. We have learned the 13th chapter, which provide you a full theory of GIS and remote sensing. However, you need to well practice the exercise provided during practical session in front of the computer. Both theory and practice allow you to deal with a wide range of GIS and application and remote sensing application to be useful for managing water resource or natural resource that you are actually to be an water resource engineer. So GIS and remote sensing is a tool for you to solve the problem related to water and natural resource.